Assalamu alaikum and hello everyone. Today we'll be presenting our discrete structure final project. I'm Junaid Ali and with me are my group members Muhammad Waqas and Sayyid Muhammad Wasik Tawfiq. So in this short video we will do five main things. We will tell you the idea behind the project, explain the maths and how we prepare the data, show the code and how it runs, show pictures that include the heat maps and the network graphs and we'll also explain them. And last we will give the main results and a short conclusion on it.
Hi, I'm Mohammed Lukas, and now I will tell you about the methodology of our project. So first of all, we categorized the data. The CPI data set contains many individual product names, and they are not always perfectly structured. So we use keyword-based categorization system. Like if the product contains a keyword food, then it will go into the food category. If it contains vegetable, it will go into the vegetable category. Similarly, for clothing, housing, transport, and many more. So these are the categories that are being shown in the report. Now let's move forward toward the time periods. We have implemented two types of time periods. You can go month-wise analysis as well as year-wise analysis. It is up to you. Next, let's go toward the data cleaning and standardization. After categorizing products, we create a city X product matrix for each time period and category. So we clean the data. First of all, if the city is missing a price or a product, we can replace it with the average of that product in that time period. That avoids empty values and keeps the data set consistent. Secondly, standardization. We standardize each product column, subtract the mean, divide the standard deviation, and in this way, the expensive products do not control the similarity results. Now let's get toward the similarity, city to city similarity, or we can call it cosine similarity. So every city becomes a vector of standardized product prices, and then we calculate their cosine similarity, which is given by the formula as being shown in the final report. Now, what does that mean? If the similarity is close to 1, that means the cities are very similar in terms of price behavior. And if it is closer to 0, that means they are very different. They have very different patterns. Now, let's move toward how we constructed networks on the basis of this similarity. So we build a city network in which each city becomes a node. Two cities are connected if their similarity is greater than the threshold. We have taken the threshold as 0.7 by default, but we can change it in our menu. The edge weight, if the edge weight equals the score or is greater than the threshold, then there would be an edge between those two cities.
Assalamu alaikum everyone. I am Sayyid Muhammad Wasik Tawfiq and I will walk through the important parts of our code for our project. So the code is implemented in Python using the following libraries as you can see in the report: Pandas, NumPy, NetworkX, scikit-learn, Matplotlib, Seaborn, Rich, and Plotly. And the script runs a menu-driven console application where the user selects a CPI Excel file and then chooses whether to see the results year-wise or month-wise. And the program then builds networks and computes city influences scores. And the menu allows the user to, as you can see in the report, view network graphs, view similarity matrices, view Hesse diagrams, top city rankings, modify the similarity threshold according to what the user needs, inspect detailed centrality tables and charts, and saves all results into a chosen directory. You can also change the centrality weighting scheme and view basic graph statistics. All right, so moving on to the main functions, the important functions that we used. So the first one is the load and structured data function. Now this function takes the raw Excel file and turns it into clean usable data. It throws away rows where the city, product, or price is missing, tidies product names, and then tags each product into a category like oil, sugar, etc. using a list of keywords. Next, it groups the data by a time period, either by a month or by a year, and for each period and each category, builds a small table where rows are cities, columns are products, and each cell is the average price. Only non-empty tables are kept, and the final result is a neat package of price tables organized by time and category ready for analysis. Then we move on to the pre-processed data function. Now this function makes each city and product price table ready for comparison. First, if any price is missing, it replaces it with the average price of that product so that we don't lose cities just because of a few gaps. Then for each product, it adjusts the numbers so that they are on a similar scale, which stops very expensive items from dominating the analysis. The output is the same table shape, just cleaned and put onto a fair scale across all products. We follow that with the build networks function. Now this function turns the price table into networks of cities. For each time period and category, it takes the cleaned city product table, compares every pair of cities, and works out how similar their price patterns are across products. It works out a similarity score. If two cities are similar enough, due to the above chosen threshold that the user chooses, it draws a connection between them in a network and stores the similarity as the strength of that connection. If there are too few cities, it just keeps them as isolated points. In the end, we get for every period and category a city-to-city network and the underlying similarity scores. Then we move on to the compute centralities function. Now this function measures how important each city is inside one of these networks using 4 different viewpoints. Degree tells us how many other cities a city is directly linked to. Closeness tells us how near a city is on average to all the others in the network. Betweenness tells us how often a city sits on the shortest paths between other cities, so it shows which ones act as bridges. And the eigenvector centrality gives higher scores to cities that are connected to other influential cities. The result is 4 lists of scores, one per measure for all cities in the network. And then we get the get entropy weights function. Now this function decides how much importance to give each of the 4 centrality measures based on how much they actually distinguish between cities. For each measure, it looks at how the scores are spread across cities. If a measure gives almost everyone similar scores, it is less useful and gets a lower weight. If it clearly separates some cities from the others, it gets a higher weight. It turns this idea into numbers using a spread measure, converts that into an information value, and finally scales these values so they add up to 1. The result is a set of weights that favor measures which add real insight. And then we get the get correlation weights function. This function also sets weight for the 4 measures, but now based on how similar they are to each other. It looks at how each centrality measure moves across cities and checks how strongly each measure is related to the others. If a measure is very similar to the rest, it is considered redundant and gets a lower weight. If it behaves differently and adds a new angle, it gets a higher weight. These uniqueness values are then scaled to add up to 1. So this method rewards measures that bring fresh information rather than repeating what others already show. Now the get centrality weights function. This function is just the switchboard for choosing how to weigh the 4 centrality measures. If we choose equal, it gives the same weight to all 4. If we choose entropy or correlation, it calls the matching function described above. If we choose interactive, it uses weights that the user has to set manually, and all the 4 weights must add up to 1. If those aren't available, it falls back to equal weights. If the method name is unknown, it defaults to the entropy approach. This lets us change our weighting philosophy without touching the rest of the analysis. And finally, the calculate final scores function. This is the final step that gives each city an overall influence score for every time period. For each time period and category, it takes the network, calculates the 4 centrality measures, and then combines them into a single score per city using the chosen weights. Then it looks across all categories. For every city, it multiplies its category score by the importance assigned to that category and adds them up. The result is one final number per city per time period that reflects its position in all the networks and the relative importance of each product category. So now Junaid will continue.
Okay, so now we'll move on to the visuals, the heat map, and the networks. So this is the similarity matrix or the heat map, you can say. Now the rows and columns here are the cities. As you can see, the bright squares, the darker, the lighter ones, the bright ones, means that they have high similarity. If a group of cities has many bright squares together, they form kind of a cluster. This means that their prices move similarly for the chosen products. And this is the network graph. Each circle here is a city. A line connects 2 cities if they are similar. Thicker lines mean stronger similarity. Node size is the degree centrality. Bigger means more direct links. Node color shows the betweenness centrality. Darker equals to more of a bridge between groups. Now the clusters in the heat map becomes groups in the network. Cities that are bridges have higher betweenness, can connect different groups. These cities can be important because price change in them can affect many places.
Okay, so let's talk about how changing weights changes the result and the hash diagram for time relations. First of all, weighting. We give the same importance to degree, closeness, betweenness, and eigenvector centralities if we are using the equal weighting method. But if we are using the entropy weighting, then this gives more weight to the metric that varies more between the cities. If betweenness varies a lot, then it will get more weight. Now what happens if we change the weighting of the system? Some cities goes up or down in the final ranking when we change the weights. For example, a city is strong, has a strong bridging power, aka betweenness centrality, will then it will rank higher under entropy weighting if betweenness varies a lot. Now let's talk about the hash diagrams. Now we compare graphs across time for some categories. An arrow from time A to time B means that the connection at time A are included in time B. The network grew or kept those edges. This helps us see if similarities are stable, growing, or shrinking over time.
All right. So finally, the conclusions. Now, the first conclusion is that the price similarity networks group cities that move together in price for a product category. The centrality measures and weighting help find the most influential cities, and changing the similarity threshold or the way we combine centralities can change the list of top cities. This is expected and useful, and it helps us test robustness. And moreover, we have also given the user the opportunity to select their own weightages, so they can play around with the values and see how it affects the final city scores. And the limitations. So the first limitation is that we match products to categories by keywords. If the product names are messy, some items may be missed, and it can pose a problem. Secondly, we replace missing prices by the average. Other methods like interpolation might change results, so the calculations may be different. And finally, category importance weights are chosen by us, so different choices change the final scores, but we have also given the user the opportunity to select weights as well. And finally, the reproducibility, that all codes, CSVs, and images are saved when you run the script. You can rerun with different thresholds or different weights to test the results. And now we are all ready to sign off. We have presented the project and hope you understand it and like it, and we will welcome questions and feedback in our presentation. Thank you.